Today we want to talk about enthalpy and something called Hess's law. It's technically Hess's law of constant heat summation, but nobody really calls it that. We just call it Hess's law. And what that says is that if we have a reaction and it occurs in steps, and most reactions do occur in steps, then if we want to know the overall heat of reaction of that particular chemical reaction, then we simply need to add up the heats of reaction of each of the steps. Kind of makes sense. Now, when we're doing this on paper, the one thing we have to do is to make sure that both the overall reaction and those constituent or step reactions match two ways. Substances have to match in how many of each of those substances there are on each side of the equation, and which side of the equation, which side of the reaction it's on. We're going to multiply or divide a step reaction to match the coefficients. And when we do, we're going to have to multiply or divide the heat of reaction value by the same factor. If we reverse a constituent or step equation, then we're also going to have to change the sign of the delta H value for the constituent equation. Last thing we're going to do is cancel out substances that appear on opposite sides of the two equations, or 3 or 4, depending on how many there are. Okay, now those rules may not have made any sense until we actually do this in a problem. So let's look at this particular one. Let me get it lined up here a little bit better. So what this says is that we have a reaction, and they may give you the overall reaction first. They may give you the overall reaction last. It doesn't matter. It doesn't change anything. But in this particular reaction, it tells us that we have two H3BO3s, and it's forming B2O3 and 3 H2Os. And we want these step reactions down here to match that reaction. So let's find something that appears only once in the step reactions. We're not going to even look at water, because look at what water does. Water is here, water's here, water's here. It'll be a mess trying to figure out what's going on with water if we try to start with this. So let's start with our H3BO3 and see if it appears anywhere or where it appears in those constituent equations. And it looks like the only place it appears is right here. That's a perfect one to start with then. It's already on the correct side of the equation, but do we have the right number? And the answer is no. What we're going to need to do is to multiply this. Notice there's two of them up here. We've got to get it to match this. So if that's true, we're going to have to multiply this by 2. Now, we can't just multiply part of a reaction by 2. If we multiply part of the reaction, we've got to multiply the whole reaction. So we're going to multiply that by 2, this by 2, this by 2, and this is my Achilles heel, guys, so be careful and make sure you do this. Make sure you multiply this last value by 2 as well. And by the way, this is supposed to be 0.020. So let's multiply this by 2. We're trying to figure out what's going to happen to these delta H values over here, because when we get done in the end, we're going to add them up, and that's going to give us our overall delta H. Okay, so let's go on. We've already said we don't want to do water, so let's look at our next one, B2O3. Where does it occur? Right here. So we've got B2O3 here in this equation. Now in this equation, we've got two B2O3s, but in this equation up here that we want to match, there's only one. Now, we can't change this reaction at all because we've already finished it. And we need to change this reaction to get it to match the B2O3. So looks like we're going to have to divide by 2 to get it to match, so that there's only one B2O3 in this step reaction. So I'm going to divide this in half, and that's going to be 1 B2O3. Strangely enough, it's going to be a half of an H2B407 and half of an H2O. And don't forget to make sure and divide this one by 2. Divide the delta H by 2. So now we've got this reaction set. Okay, we have found this substance and set it. We have found this substance and set it. Everything else in the reaction has to do two things. We have to get all the waters to add up to 3 waters, and everything else has to cancel. And that's going to help us figure out what to do with this middle reaction. Because if everything but the waters has to cancel, and I'm going to underline the waters so we can see where they are. The first thing we notice is that the water in this middle reaction is on the wrong side. So what are we going to have to do? We're going to have to cancel, or not cancel it, we're going to have to mark that out and rewrite it in the opposite direction. Now, guys, do not try to do this without rewriting it. Taking shortcuts on Hess's law problems will get you in quick trouble. So mark it out and actually rewrite it. Try to keep your arrows in the same position. It will really help when you're trying to figure out what's on which side of the equation. So let's rewrite this. We've got, when we rewrite it, we've got 4 HbO2s. And we've got it forming H2B4O7 plus H2O. Now, as soon as we reverse that reaction, we've got to go back up here and do what? Change the sign. Don't forget to do this. So this becomes positive instead of negative. And that's very important. That make a big difference when we add these up in the end. Also, let's look at what's going on here. When we rewrite this equation, right now we've got 2 waters here, another half of a water here. We want a total of 3, and right now we've got 3.5 waters. And let's look at something else. Everything else is supposed to cancel, and notice we've got 4 HbO2s here, but if you look back up here, we've only got 2. So it looks like we're going to need to divide this reaction in half. When we divide this reaction in half, we'll get 2 of our HbO2s. We'll get a half of an H2B4O7, and we'll get half of a water. Now, what does that do for us for our waters? Very nicely, we now have 2.5, 3 waters. So that matches our 3 waters in our compound. And if we want to double check ourselves, it's always a good idea to do this. You don't have to, but it's a good idea to check to see if everything else cancels out. And they can only cancel out if they're on opposite sides of the equation. Otherwise, they'll add up. So let's look what happens. We've got 2 HbO2s here and 2 HbO2s down here. It looks like these are going to cancel because they're on opposite sides of the reaction. We've also got a half of an H2B4O7 here and another half on the other side of the equation. Those are going to cancel. So as you can see, everything in here has either been circled or canceled, which is exactly how we want to end up when we have one of these Hess's law problems. So one thing we also need to do, and I told you it was my Achilles heel that I almost forgot to do. What did I forget to do when I halved that reaction? Yeah, I almost forgot to go over here and half the reaction on the delta H values. So make sure you do all of that. Now, so what we're going to do next is to simply add all of these up. We're going to multiply this one by 2. We're going to divide this one by 2. And we're going to divide this one by 2 and then add them up. The only one that's negative now is the top one. When we get done, we should end up with 14.4 kilojoules for our heat of reaction. And since it is for a specific reaction, 14.4 kilojoules, you could say per mole RXN. So I'm going to go ahead and just erase that and write it over a little bit so I have some room. 14.4 kilojoules per mole RXN. There you go.